Alright, today we're going to make a Taylor polynomial for the sine function. There is a cookie cutter way we can do this, where I can give you a formula for all the coefficients in the general form, but I'd like to take a slower approach, so perhaps to look at the general idea behind it. In particular, the formula that you may have seen or may not have seen is based on a technique called matching derivatives. And so the idea is you have to have a place where you want to build this polynomial, and I picked rather arbitrarily 2 pi over 3. And then you have to comply with this notion that the polynomial p and the function sine will return the same value at 2 pi over 3. The polynomial and the function will have the same derivative at 2 pi over 3. They will have the same value for the second derivative at 2 pi over 3, and so forth. Now, this is related to a concept I think you've probably seen before, which is just linear approximation. When you find the tangent line to a curve like sine, it turns out you're actually on your way to making a Taylor polynomial, especially if you use the point-slope formula for a line, and that's the approach we're going to take today. So let's get started. Up on this sine curve, there's a point P. And that point P is located right here. It's the point of tangency for this tangent line. It has an x value of 2 pi over 3. And it's got a y value of the sine of 2 pi over 3, which is root 3 over 2. And I put this little graphic up here to remind you, just in case you don't remember all your unit circle values. We're going to need that cosine too later, but not yet. Okay, so for a point like P, you want to write a point-slope equation that generally has a form like this. And we already know two of the things that we need to inject into this form. We know the x and the y for the point P. This is the x, this is the y, so I'll put those in there now. So it's y minus root 3 over 2 equals, and then I'll skip that for a second, and it's x minus 2 pi over 3. And finally, just like in the slope-intercept equation, y equals mx plus b, in the point-slope form, this m refers to slope. Now in calculus, slope, of course, is found by the first derivative. A tangent line's slope is the first derivative evaluated at the point of tangency. And so we're going to do something like this. We're going to take our function, sine, that's f of x, and we're going to get its derivative, f prime, which of course is cosine. And then we're going to evaluate the first derivative at 2 pi over 3. So that's cosine 2 pi over 3, which is negative 1/2. See, right up here, negative 1/2. That is the slope of this tangent line. And that's the value I'm going to put right here as the multiplier of this little binomial. So if you're not used to this form of tangent line, it's just another way to do them. It's my favorite because it's basically just have to drag and drop a few things in there and you're done. Now, I'm going to change the form of this just slightly to get this thing rolling. One, I'm going to add root 3 over 2 to the right. So there'll be nothing over here anymore except the y. And the root 3 over 2 will go to the right and it'll be positive. I could put it here or here. And then the other thing I'm going to do, 2 steps at once here, because you kids are accelerated, I'm going to take the y out and put p of x there, which will stand for the polynomial p. So that's going to look like this. P of x equals root 3 over 2 plus negative 1/2 x minus 2 pi over 3. Okay, first a couple comments about this. You can use this tangent line formula for linear approximation. And I want to do that in case you haven't seen that before. Okay. here comes the sine curve, and here is that tangent line. They put out similar y values as long as you stay close to where the tangent is tangent. You get too far away and you might not get very good values. But if I go trace onto the sine curve at a value of 2, the sine there is 0.909 roughly. And if I go to the tangent line and trace to 2, I get 0.913. It's higher. Not much higher. It's only 0.004 higher. 4 thousandths of a unit off. That's a pretty good approximation. On the other hand, if you get too far away from that point of tangency where x equals 2 pi over 3, you might get some really bad values. So let's go back to the sine, and let's trace to the sine of 1. And of course, the domain here, the angles are all in radians, okay? So at 1, the sine is 0.84. Now go to the tangent line and trace to x equals 1. And you get a much, much too high value of 1.41, which is about 0.6 units too high of something that was only 0.8 in the first place. That's called roughly 75% error, and that's terrible. Okay, well, what if we had a way to take this tangent line and bend it? Maintain the point of tangency and just sort of bend the tangent line around that tangent point. And I'm just going to use a piece of cable here to show that. It would look something like this. So what we're looking for is a parabola that's inverted, that's sort of, I don't know, tangent to the curve in the way that the tangent line is. And because it's inverted, it needs to have a negative coefficient, leading coefficient on the x squared term. Now let's study this for a minute, because there are clues here that we can follow. What was this? Why, that was the value of sine at 2 pi over 3. So that's f of 2 pi over 3. And what was this? Well, that was the tangent line slope, but that came from the first derivative of the sine. That is f prime of 2 pi over 3. So it's not too big of a stretch to think that if we were going to have another term on here that looked like this binomial, but it was quadratic, it would look something like this. You'd have root 3 over 2, you'd have negative 1/2, x minus 2 pi over 3 to the first, if you will. And then you'd have another term here that would look something like this. X minus 2 pi over 3 squared. And I mentioned that we need a coefficient here that was negative to get that parabola to be, sort of flipped upside down. What might this be? Well, if you study up here, there's a pattern. This was f of 2 pi over 3. This was f prime of 2 pi over 3. It could very well be the case that this is just f double prime of 2 pi over 3. Well, that's almost true. I went ahead and looked up f of double prime of 2 pi over 3. It's in this table here. F of x is sine, f prime is cosine, f double prime is negative sine. So I need to evaluate negative sine at 2 pi over 3, and I get negative root 3 over 2. Okay? If you put negative root 3 over 2 here, which I'm not going to do, you'll get something like this. And then we'll have to decide how good this is. It is an inverted parabola. It does contact the sine curve at the point of tangency. I think it looks pretty good. But it turns out if you divide by 2, if you take the second derivative, evaluate it at 2 pi over 3, which was negative root 3 over 2, and if you divide it by 2, you'll get something even better. And I've got that ready to go too. Trying to be respectful of your time here. Let's turn this one off. Oops, let's turn this one off. Let's turn this one on. And you tell me if this looks better. It does a great job of hugging on to that sine curve. At least better than the one I saw before. So we're going to divide by 2. Now what's the mathematical reason for dividing by 2? I'll show you. Let's pretend for a minute we don't know what this is, and we're just going to call it A. So here I have, and I put a subscript of P2 on here, and that just means second degree or quadratic. But otherwise, this is exactly what you saw a minute ago, with an unknown coefficient of A here. Okay, let's take the derivative. The derivative of this constant is 0. The derivative of this linear term is 1 times the multiplied constant -1/2. So you just get -1/2. The derivative of this second degree term is 2 times A times this binomial to the first power. And you're done with the first derivative. Now let's take the second derivative. Well, this is gone. This is a constant. When you take the second derivative, it's gone. And when you take the derivative of this term to get from the first derivative to the second, you're going to multiply 1 times 2a and lower this to the 0 power. And you're going to end up with just 1 times 2a, which is a constant. So a couple important ideas here. When you have a quadratic polynomial, by the time you get to the second derivative, there's no variables anymore. It's a constant. And in this case, it's a negative constant. And why is that? Well, remember, we need our polynomial to have exactly the same second derivative value at 2 pi over 3 as our function does. And we looked up our function's second derivative at 2 pi over 3, and it was negative root 3 over 2. So putting all these ideas together, the second derivative, sine's second derivative at 2 pi over 3 is negative root 3 over 2. And I need these two things to be equal. The polynomial and the function have to have the same value of second derivative at 2 pi over 3. Well, if these are equal, then that coefficient a cannot be this, because 2 times that coefficient a is this. And that means to get a, this has to be divided by 2. And that's why I divided by 2. So I'm going to take the second derivative, evaluate it at 2 pi over 3, get negative root 3 over 2, and I'm going to divide that by 2. And that was the polynomial you saw on my calculator just a second ago. Well, if a quadratic polynomial is a big improvement on a linear polynomial, maybe a cubic polynomial would do even better. And it's not the most ideal thing in the world, but it's the best thing I could come up with teaching remotely today. Remember how I said that the parabola has a constant second derivative? That means it's always going to have the same kind of concavity. When that second derivative is negative root 3 over 2, I guess it was. That was the signs anyway. You'll always have downward concavity, but the sign doesn't do that. The sign changes concavity as we move to the right from our point of tangency, and it reverses to upward concavity, as you can see right there. In order to make that happen, you cannot have a constant second derivative. You have to imitate what the sign is doing. The sign is concave down here. That's a negative second derivative. The sign is concave up here. That's a positive second derivative. If we go from a negative to a positive second derivative, that must mean the second derivative is increasing, and that must mean the third derivative is positive. Okay. Well, I'm trying to motivate what comes next here. And that is, let's go for a third term. So we'd have root 3 over 2, negative 1/2, x minus 2 pi over 3 to the first, plus we just got this one, which was negative root 3 over 2 over 2, emphasizing that I had to divide by 2 there. And this was squared. Our new term is going to look like this. It's going to be x minus 2 pi over 3 and cubed. But what will be the coefficient here? Studying what we've seen so far, the constant term was f of 2 pi over 3. The linear term was f prime of 2 pi over 3. The quadratic term had a coefficient of f double prime of 2 pi over 3, but we had to divide by 2. Okay, it's pretty hard to infer the pattern, but if you think this is f triple prime of 2 pi over 3, you're right. If you think that we have to divide it by something, you're right about that too. But what? What do we divide by? This 2? It's not quite good enough. So let's take another look at our new polynomial. And let's just admit that we don't know what this coefficient is, so we're just going to call it b. And I wrote all this out in advance to try to make this video under 20 minutes. We'll see if it works. There it is. Isn't it beautiful? We want to take a first, second, and third derivative and keep track of mostly what this one does, because the rest of these are all going to vanish. We already talked about in the first derivative, the constant term goes to 0, the linear term goes to a constant, the quadratic term goes to a linear term, etc., etc. Keeping your eye on this one, just in the first derivative, I'm multiplying here by 3 against whatever that coefficient b is, and I'm still quadratic. Okay, let's get to the second derivative. That constant goes to 0. That's why you don't see it down here. This, which is really root 3 over 2, negative, becomes the derivative of that term, because that's a linear term, and it has a derivative of 1 times its coefficient. And now this term, which was cubic and is now quadratic, and we're going to the second derivative, we're going to multiply 2 times 3 times b, and then lower the power to 1. So that would look like this. You can put a 1 here if you want. Now to get to the third derivative, this, which originally came from the quadratic term, is now constant, and it's going to go to 0. So the only thing we have to fuss with is this. So if you want, multiply 1 times 2 times 3 times the coefficient b and lower this to a 0 power. Strict application of the power rule. And this is what we're left with. The third derivative of this polynomial, at least if it's just a cubic polynomial, looks like 1 times 2 times 3 times b. And there's no place to plug an x. So what does that mean? It means that this is a constant, and it also means that you can't plug 2 pi over 3 into it. So the polynomial, which should have subscripts of 3 on it, I apologize for that, because it's third degree at this point. Its third derivative at 2 pi over 3 is just 1 times 2 times 3 times b. All right, let's go all the way back to the table where we had all those derivatives of our function f, which is sine. And let's go to the third derivative, which is negative cosine. Let's plug 2 pi over 3 into that, and we get positive a half. So, writing that down here, I have the third derivative of the sine function evaluated at 2 pi over 3 is supposed to be a half. And this are supposed to be equal things. So, can f triple prime of 2 pi over 3 be the coefficient that goes here? No, not unless you divide it by 2 and 3. That's what you're supposed to learn here, and that's what we mean about matching derivatives. So this value is a half, and yeah, I'm going to put it here, but I'm also going to divide it by 2 and 3. I could just divide by 6, I guess, but that wouldn't fit with the overall pattern. Yes, you may recognize this as 3 factorial. And you may recognize this as 2 factorial. And if you wanted to really extend the pattern, you can divide these by 1 and 0 factorial respectively, because those are just values of 1. Okay, We're at 20 minutes. Time for the big reveal. Here is our Taylor polynomial for sine, evaluated around 2 pi over 3, or expanded around 2 pi over 3. Today we got about this far with it. This is what the next term looks like. And this is completely unnecessary, but I was goofing around on Desmos, and I decided to write a 16th degree polynomial for the very thing we worked on today. Here it is. And this is tedious as all heck, I can promise you. But once you type it in, Desmos handled this in a fraction of a second. It gave me this curve, and look at this curve. Okay, sine's the heavy-looking one, and a polynomial is the gray one. And it looks like they merge almost perfectly right around x equals -4. And we have really good fidelity all the way up until about x equals +8. So we've expanded through a very wide interval the usefulness of this Taylor polynomial by doing what? Throwing lots of terms in there. Okay, now let's get to the general form. Today we had x equals c of 2 pi over 3. And that is why we had the function value, the derivative, the second, third, and so forth derivatives of sine evaluated at 2 pi over 3. Also, we had all these binomials that looked like x minus 2 pi over 3. And here was one where we squared it. But you can do this anywhere you want. You just have to pick the c, and then you have to go for it. Okay, the last thing I need to mention, and I'll try to be fast. What happens if you take this general Taylor polynomial for a very specific and frequently visited case of c equals 0? The first thing you would notice is that this would be f of 0, f prime of 0, f double prime of 0 divided by 2 factorial, f triple prime of 0 divided by 3 factorial. So that would be an important change. The other thing is all these binomials would look like x minus 0, x minus 0 squared, x minus 0 cubed. And there's no need to write x minus 0 when x minus 0 is just x. So then you would get a specific example of a Taylor polynomial. It's still a Taylor polynomial. But it doesn't look nearly as complicated. For one, you don't have all these little binomials. You just have powers of x. Otherwise, really is the same thing. You still have to remember that on the quadratic term, from there out, you have to remember to divide by factorials that match the powers. And I think that's going to be enough for today. Thanks for listening. My name's Eric. Have a good day.